We've now got all the analytical tools put in place necessary to analyze exactly what's happening when a voltage and current wave travel along a transmission line, at least in the DC case. And what I'm showing here is that we've got a pretty typical circuit. We've got a battery that's got some sort of internal resistance associated with it. It's connected to a transmission line through a switch. That transmission line connects the battery to some sort of load, and what we want to do is just fully analyze what's happening in this circuit. And when I close this switch, a voltage and current wave are going to propagate from the input end of the transmission line, or be established, I guess, at the input end of the transmission line. And they're going to propagate along the transmission line towards the load end. The nomenclature is that the voltage at the input end of the transmission line as a function of time is just v of 0 comma t. We've replaced the distance with a 0 because it's the input end. And similarly, the current at the input end of the transmission line is I of 0 comma t. Those sinusoidal patterns, or in this case a DC signal, is going to get impressed onto the transmission line and propagate along the length of the transmission line. That propagation time is going to again be t equals the length of the transmission line divided by the propagation velocity of the electromagnetic wave in the transmission line, mu sub p. And the current and voltage waveform that is established at the output, or the load end of the transmission line, is given the terminology v of d comma t and I of d comma t, just indicating that it's at the load end. V of 0 comma 0 is the initial voltage. It's the very first voltage that's imparted at the transmission line at time t equals 0. And then we've got one more nomenclature, v of x comma infinity, which we're just saying at any point along the transmission line, what's the value of the voltage when t has got really, really large, and we call that the steady state value. And what is happening in this transmission line is when the switch closes, a voltage waveform is launched from the input end to the output end. It will then reach an impedance boundary here. And that's what I'm showing with this line. It takes d over mu sub p seconds to reach that impedance boundary. At the impedance boundary, it might be reflected. It depends on whether or not that's a non-zero reflection coefficient. If that is non-zero, there will be a first reflected voltage wave. Its value will be the voltage reflection coefficient times the value of the first forward voltage wave. That will also take 1d over mu sub p seconds, which means that the first reflected voltage wave reaches the input end of the transmission line at a total of 2d over mu sub p seconds. When it reaches this impedance boundary, depending on the value of the reflection coefficient at the input end of the transmission line, there may be another voltage reflection. If there is, the total value of the reflected voltage signal will be source voltage reflection coefficient times load voltage reflection coefficient times whatever the first forward voltage wave was. So that's this line here. That behavior can just repeat itself over and over and over, with each time required for one transversing of the transmission line being d over mu sub p seconds. So I think we've repeated that example or analysis enough that we can get into an example. And what we have here is we've got a 60 volt battery with a source resistance of 50 ohms, and it's connected to a load via a 200 meter long transmission line. The known characteristic impedance of the transmission line is 50 ohms. We would have determined that from the distributed parameter models. And the propagation velocity is 200 meters per second, which we can determine from the material properties. What we're asked to do is plot the voltage at the x equals 0 interface and the x equals 200 meters interface as a function of time for the following resistances. And I've rewritten them over here. In part A, RL is going to be 50 ohms, RS is going to be 50 ohms. In part B, RL is going to be 25 ohms, and RS is going to be 50 ohms. And in part C, RL is going to be 250 ohms, and RS is going to be 50 ohms. So these are the three conditions that we're going to analyze in this example. So the first thing that we will do is calculate the initial value of the voltage waveform V of 0, 0. This is the voltage at the input end, the second that the switch, the instantaneous second that that switch is closed. And the value of that is going to be determined by the voltage divider between the characteristic impedance and the input, or in the source resistance of the battery. So it's going to be a voltage divider of Z0 over Z0 plus RS. And the battery voltage is 60 volts, and we're going to multiply that by 50 over 50 plus 50, and that's going to give us a value of 30 volts. And again, that'll always just come from the voltage divider between Z0 and the source resistance. The reason for that being is that the characteristic impedance, remember, is the value that the battery will see of the circuit impedance before any propagation has occurred. We also want to calculate how long it takes the signal to get from the input end to the load end, and so that's the one-way propagation time t, and that's just the length of the transmission line d divided by the propagation velocity mu sub p. So that's 200 meters. That's the length in this one, and the propagation velocity was 200 meters per microsecond. So that is just a one-way propagation time of 1 microsecond, or 1 times 10 to the minus 6 seconds. So now we can begin to do these analysis because we have these numbers. We'll start with load resistance of 50 and source resistance of 50. What we'll do is we'll calculate our voltage reflection coefficients. That's ZL minus Z0 over ZL plus Z0 at the load. So that's, in this case, 50 minus 50 over 50 plus 50, and that is equal to 0. And the reflection coefficient of the source is going to be ZS minus Z0 over ZS plus Z0, and that's equal to 50 minus 50 over 50 plus 50, and that's also equal to 0. So there's no reflections occurring in the circuit. So if we were to plot on the bounce diagram what's happening here, we have our horizontal axis, which represents distance. We have our vertical axis, which represents time in seconds, distance in meters. This input end is 0 seconds and 0 meters. This is 200 meters. And we know that it takes increments of 1 microsecond for waves to propagate. So what we showed is that the voltage at the input end, where did we do that? The voltage at the input end is 30 volts. So what happens is we get a 30 volt wave that takes 1 microsecond to get to the other side. When it reaches there, there is no reflection coefficient, meaning all the voltage is transmitted to the load. So this is 30 volts. There is no reflected voltage, for there is no first reflected voltage wave. So that's the entire voltage on the transmission line. We were in the problem statement asked to draw this, or to plot the voltage at the input end of the T-line as a function of time and at the load end of the T-line as a function of time. So we use the bounce diagram to do that. This will be V of 0, T, the input end of the transmission line. This is T. And so if we were to look at the input end of the transmission line, what we do is we sum up all the forward and reverse voltage waves for that distance, and we see that there is only one voltage at the input end of the transmission line. That's a result of there not being a reflection. So what that means is that at t equals 0, the input end of the transmission line was initially at 30 volts and it never changed. It's constantly 30 volts. Now what about V of 200, t? Well, we sum up all the forward voltage and reverse voltage waves, and we see that there isn't a voltage wave that appears at the load end of the transmission line until 1 microsecond. So up until 1 microsecond, the value has been 0 volts. At 1 microsecond, the value jumps up to 30 volts. So what we see in the matched case when RL equals 50, Z0 equals 50, and RS equals 50 is that at the input end, the voltage at the transmission line immediately rises to 30 volts, which was half the battery voltage due to the voltage divider. At the load end, we see that there's a delay of 1 microsecond before any voltage appears on the transmission line. So we're already starting to see how electromagnetic theory applies, and you would have never analyzed this in a circuit analysis course. So now let's move on to the case where RL is equal to 25 ohms and RS is equal to 50 ohms. You can already tell that there's going to be a reflection at the load. So what we need to do is recalculate the reflection coefficient at the load, and that's going to be 25 minus 50 over 25 plus 50 ohms, and that's equal to minus 1/3. The reflection coefficient at the source hasn't changed. It is still 0, and the input voltage hasn't changed. V of 0, 0 is equal to 30 volts. This hasn't changed because we didn't change this value here, and this hasn't changed because we didn't change this value here, and the characteristic impedance has stayed constant. So all that's changed in this analysis is the reflection coefficient at the load is minus 1/3. So let's draw the bounce diagram for reflection coefficient at the load being minus 1/3. The bounce diagram is going to end up looking like something like this, where we've got t equals 0 seconds and d equals 0 meters here, and this is d equals 200 meters. And what's going to happen is we've got this 30 volt wave that propagates towards the load end. It reaches the load end at 1 microsecond. When it gets there, it's going to get reflected back towards the source. The value of this voltage reflection is going to be the reflection coefficient at the load times the voltage. So negative 1/3 times 30 volts. This is going to be a negative 10 volt wave. When it reaches this end, the reflection coefficient is 0, so there is no further reflection. So if we were to translate that into our plots for voltage at the input end as a function of time, we see that the voltage at the input end is 30 volts initially. It remains 30 volts until this time when the first reverse voltage wave reaches the input end, which is at 2 microseconds. So it will remain 30 volts until it reaches 2 microseconds. At 2 microseconds, the total voltage is 30 volts plus minus 10 volts, so 20 volts total. And there are no reflections, so we know that it'll always be 20 volts. Now let's look at what happens at the load end. So a plot of V of 200 comma t as a function of distance. There is no voltage at the load end until we get to 1 microsecond. So at 1 microsecond, we see that the 30 volt wave reaches the load. However, instantaneously a reflection is generated that is minus 10 volts. So at 1 microsecond, we get 30 volts plus minus 10 volts is 20 volts. So very different behavior on the input end versus the output end. Initially, for 2 microseconds when we close the switch, the input end of the transmission line actually reads 30 volts. It doesn't settle down to 20 volts until 2 microseconds is reached. And at the output end, there's a 0 voltage for 1 full microsecond, and then the voltage rises to 20 volts for infinity after that. Our last case was that we had an RL equal to 250 ohms and we had a source resistance of 50 ohms. Again, our input voltage and our reflection coefficient at the source are going to stay constant. What will change is the reflection coefficient of the load. That's now 250 minus 50 over 250 plus 50, which gives us a value of positive 2/3. If we translate that into a bounce diagram, so this is 0, this is 200 meters, this is distance, this is time. We've got an initial voltage wave of 30 volts. It is reflected at the load end with a reflection coefficient of 2/3, so 2/3 times 30 is a 20 volt signal gets reflected back. And at the input end, the reflection coefficient is still 0. So all reflections cease. So if we were to plot this, what we would see is that voltage at the input end of the transmission line, V of 0, t, it's initially 30 volts, and it stays 30 volts for a full second, and it doesn't see the impact of this 20 volt signal until 1 microsecond, 2 microseconds later. So what's going to happen is we're going to go from 30 volts to 50 volts at 2 microseconds. If we were to look at the load end, what we would see is that V of 200 meters, t as a function of time. There's no voltage until 1 microsecond, and then at 1 microsecond we get both the first forward wave and the first reflected wave, which are a total value of 50 volts. And that occurs at 1 microsecond. And there's something interesting that I'd like to point out. If we were to ignore electromagnetic analysis and just use circuit analysis on these, meaning we would ignore the effects of the transmission line, our first circuit would have looked like this. No, all our circuits would look like this, where we just have removed the transmission line, and this was a 60 volt battery. So it's just a voltage divider circuit is all we've been analyzing. And what we've been plotting, let's say that we plot the voltage at the load. In the case of the 50 ohm resistor, VL would have been equal to 60 times 50 over 50 plus 50, which is equal to 30 volts. In the case of the 25 ohm load, VL would have been equal to 60 times 25 over 50 plus 25, which is equal to 20 volts. And in the case of the 250 ohm load, VL is going to be equal to 60 volts times 250 over 50 plus 250. And that would give you 50 volts. So if we ignore electromagnetic analysis, these are the voltages we would have gotten at the load for those conditions. And if we go look up at our plots, we see that our plot for the load is 30 volts. Our plot for the load steady state is 20 volts, and our plot for the load at steady state is 50 volts. 30, 20, 50 volts. They're the same values. What electromagnetic analysis allows you to do is really to determine what's going on in the intervening times before steady state. So in all the cases, the electromagnetic analysis reaches the same steady state value as circuit analysis techniques do. However, it also gives you this transient information right here that traditional circuit analysis doesn't provide for us.